Introduction. Today is Sheshank Mageshwar, is that right? And he's definitely livened up things since he's been here. In fact, his whole graduating class has really livened up things. He's been the most active graduate student group we've had in a long time. And it's been a delight to have him in the lab. I read through his CV before this, and before he got here, it's interesting that he took a year off in 2016 to 2017 to teach a 4th grade classroom as part of City Year, which was really impressive to me that he had the wherewithal to do that before taking on graduate work. He's also quite a citizen of the world, I have learned. He was born in India, spent a little time in Singapore as a child, and I guess now holds dual citizenship, so who knows where he's going to end up globally in the long run, but all doors are open. He got his undergraduate degree at University of Oregon, the other end of the country. He got a BS in human physiology, and then came here and has been working on an MS in human physiology. Oh, and I wanted to mention he also has a minor in biochemistry, which I didn't know until I read the CV. But today he's been working on the brain in a different way than is usually done. I think you'll find his work interesting. He's given us the title, Sex Differences in Cerebral Microbleeds in Aging C57 Black 6 Mice. Take it away.
I'm sure the film was still on. Sam was still going to do that too. Hi everyone, thank you Dr. Morgan for a wonderful introduction. Again, my name is Sheshank Mageshwar. Most of you all know me. I've wandered the 4th floor, probably a couple centuries, if you will. Today my talk is going to be about the master's work I've done in Dr. Morgan's lab. It's sex differences in cerebral microbleeds in aging C57 black mice. Before I start, I'd like to put out a dedication. I put it in my thesis, but I want to put it out in the presentation too, because it's really important to me. One of the dedicates to the thesis and my presentation to my sister and my departed dog, Knight. He's like a little brother to me. Both have really pushed me throughout my growing up, and even today, my sister wished me luck, and was there when I was down. So, and it also made me want to do better. So this is kind of for them as well. So the outline for today is really simple. We're going to start off with the purpose. I'm going to tell you why I did this in the first place. What's the purpose of doing this? And then we'll go into the background. And then we're going to talk about the hypothesis. And then from there, we'll talk about the methods of how I did it, and then results, conclusions, and then future directions, and give some acknowledgments at the end. So the purpose of this thesis was simply to identify the aging effects of cerebral microbleeds in female C57BL6 mice, and then using this data to compare that to work done previously in the lab and comparing it to the male side of things as well. So looking at the sex differences. All right, and there's a big reason why we started doing this too, and it has to do with looking at dementia, looking at cognitive decline as you age. And dementia is an umbrella term for a group of diseases that are associated with memory decline and overall reduction in a person's ability to perform daily activities. And it's important to note that this disease is now being shown to be a progressive disease rather than being a complete sudden onset. And with that said, it's important to understand mild cognitive impairment, or MCI, because this is being kind of said as the mark between what's considered normal cognitive ability and what is considered dementia. And important also to note is there are CVD risk factors that can be associated with this as well, and this can be measured through pulsate velocity, which is something that we do in our lab. And this is shown to be another precursor for dementia. The most common type of dementia is Alzheimer's disease. or Alzheimer's dementia. It's important to note that Alzheimer's dementia and Alzheimer's disease are kind of considered a little separate. Alzheimer's dementia is kind of part of the continuum for Alzheimer's disease. This was first diagnosed back in 1906 by Dr. Alzheimer's because, well, he named it after himself, which makes sense. And there's two major hallmarks for Alzheimer's disease, dementia. It's beta amyloid plaques and tau neurofibrillary tangles. Vascular dementia is a little different, and it's considered the second most common type of dementia. And it's memory loss due to vascular damage or vascular injury in the brain. And part of this also includes CVD risk factors that can lead to mild impairments, which can then lead to dementia pathology. So now it's important to understand that kind of comparing why we have a difference in Alzheimer's disease and vascular dementia. And this kind of keys into the point of why we looked at cerebral microbleeds in this study. Both share a lot of similar symptoms, and a lot of drugs that are used for vascular dementia are also the ones that are used for Alzheimer's disease as well. However, it should be known that both the drugs that are used are not, they're still kind of not, are still in testing phases, and many have also stopped at phase 3. Many of the drugs have looked at tackling reducing beta amyloid plaques or tau tangles. However, one study that I mentioned here that uses the drug solazumab, I can't say the name, I'll be honest, it's solazumab, I'll try my best. It looks at decreasing beta amyloid plaques, and they did decrease, but they found that cognitive decline is still present. So that shows that these drugs that are used are not actually directly affecting or not helping fully the dementia pathology. So researchers looked into looking at tau tangles and tau fibrillary tangles as well, but those drugs that are coming out for those are not are still kind of stopped at phase 3 because of potential negative side effects. This brings us to looking at the vascular pathology. So even back in 1906, when Dr. Alzheimer's looked and saw diagnosed Alzheimer's, he did see that the brain had vascular damage. So this kind of brings to the point that potentially there are vascular pathology that should be noticed or known to help for understanding new effective mechanisms to treating dementia in general. This brings us to cerebral microbleeds. Cerebral microbleeds are just a type of small vessel disease and it's also known as microhemorrhages. And previous studies have shown that CMBs are connected to lower cerebral blood flow in the brain and also cognitive decline, which can lead to dementia pathology. In human studies, it's been shown that damage to the aorta can lead to these cerebral microbleeds, and that increase in pulse wave velocity is associated with microvascular damage and to cerebral small arteries. And then in 2012, which seems like a while ago, CMB was connected to cognitive decline as well, and this was confirmed through MRI studies and cognitive tests. And it's important to look at the mouse model in this case. In the mouse studies, we see that when hypertension was induced, C57 black 6 mice had increases in CMB levels. So it was thought that hypertension kind of led to that. However, it was also found later there we go. So all I wanted was just that one thing to happen. It was found in our lab that aging itself can also lead to increases in CMBs without inducing hypertension, which is kind of what led us to help us understand this in the female model. And this brings us to sex differences. Now the NIH is now, about around 2014, has mandated that sex differences becomes a prominent piece in research. And this is important because it allows us to understand the differences between the sex, understanding if there's different mechanisms. And research is now currently coming out more and more, but it's still in its early stages. And it's important that people take it up, especially since the NIH is now funding it. All researchers want to get the money for that. So important to look into that. That was a really bad joke. I'm sorry. But this is also useful in research and clinically because it allows to us to understand the potential improvements and effects of different sexes. One thing I should want to note is that sex is different from gender. Sex is the biological difference between male and female, while gender is what's considered isn't a social identity that someone can consider themselves. So when looking into research, looking into identifying pieces throughout this talk, you'll see that I never say sex instead of gender, and that's something that researchers should start doing as well. So with this, looking at, some research that's come out for aortic stiffness has shown that in humans, there are lower aortic stiffness between puberty and up to menopause. But then this flips once menopause hits, and that females actually have a higher aortic stiffness post menopause. And in the mouse model, the same thing kind of seen, that females are less susceptible, but at old age just becomes attenuated. In terms of dementia, we're seeing that humans, we see that research points that old females are more susceptible to myocarditis. Old females are more susceptible to MCIs and dementia compared to males. But it should be noted that in humans, males do end up dying a little earlier than females, so that could be a potential reason why we see more women with dementia pathology and incidences of myocardial impairment. This brings us to aging, and it's important here. I want to talk about why do we choose the C57 black 6 mice model. This model has been shown to be good for aging because it allows us to be, there's well enough research to show us the survivorship of the mice going up to a point where we can see the aging differences at an old age. It's also the basis for many knockout mice models that are seen right now. Work by Flurkey et al. Has, in a book he helped write, shows us the comparison of ages between humans and mice. And so what is shown is that young adults, a young adult human male is compared to a young adult human at around 3 to 6 months. And then middle age is around 10 to 14 months, and then finally old age is 18 to 24 months. I put asterisks there because you'll find out I talk sooner or later that I actually, in our research, we actually use middle age around 17 to 18 months, and old age of 24 to 25 months. And the reason why this is still considered all right to do is because other prior research has shown this is as they've used these age ranges, as well as the fact that we look at sexual maturity, because sexual maturity is another aspect that is important for my study to understand. It should be noted that both sexes kind of do hit puberty around 10 weeks in the mouse model, and that female mice can reach sexual maturity earlier if in the presence of sexually mature male mice. But we don't start seeing any degradation or complete senescence of reproduction or of the hormones until 18 months of age. And so that's kind of the reason why it's possible for us to use the middle-aged mice of being 17, 18, because that's when we can start seeing those pre-menopausal kind of declines, and they call it instead of the middle age for in this study. And then past 18 months is when we can start talking about the old age. Part of that too, in talking about senescence, aging is considered a time-dependent change, and it's very predictable, while senescence is specific time points of aging that we see from aging dysfunction. So with this, I want to go back to the purpose and then back to our hypothesis. The purpose again was to identify how cerebral microbleeds increase, or if they increase in female C57 black 6 mice, and then comparing that to the males. It was hypothesized, I hypothesized, that females would have an increase in these bleeds with age, and then that and then this would actually be, and then in the male mice you actually see more bleeds until old age, where they start becoming attenuated and almost the same. So this kind of leads me to my materials and methods. So the way we do it is we can work with Cephas and black 6 mice, so then a few times. And the age cohorts we use are young at 3 to 5, middle 17 to 18, as I said earlier, and then old 24 to 25. It should be noted that each cohort has an N of 6. Except for the N for the old, we also had a positive old male control, and that had an N of 3. All procedures were for animal anesthetization and tissue distraction was approved by the ICOOC of Boston University. From this, so the first step for us to do was to essentially sacrifice the mouse, perfuse the C57 black 6 mice. So first we anesthetize the mice with isoflurane, and then we do a transcardiac perfusion where we insert a needle into the left ventricle of the heart, and then make a small cut into the right atrium to allow the blood to flow through. And then 1x PBS, which is phosphate buffer saline, is then pumped through to clear out the blood, and then paraformaldehyde is then put in afterwards to help fix the mouse. Successful perfusion was shown if the liver was fully bleached, essentially white, and if the body was completely hard. Another good way to look at it was if sometimes the mouse, if it has tail move while it's going, just making sure that everything is fully fixed. From there, we do a brain extraction where we essentially, as you can see right on the side there, that is the head of the mouse, and right before the brain extraction occurs. And in this, we essentially open up the skull and carefully cut open the skull and remove the brain and put it into a sensation vial full of paraformaldehyde. Then to prepare the tissue, 15%, 30%, and another around 30% of sucrose PBS was used to help make sure the tissue was prepared and ready for freezing and cutting later on. So brain freezing occurred simply by using 2-propanol, which is put in dry ice. And after about a minute or a minute and a half inside the dry ice, the brain was taken out of the propanol and it was ready to freeze in -80 degrees. After this is done, about 24 hours later, or since it is frozen, you can wait a little bit if you need to. You can start cryosectioning. I use the Lycosium 1850 cryostat machine and make 15 micron thick slices. And then from there, I put these sections into a 24-well plate that was full of antifreeze solution. And then this was placed in -20. From there, I would actually, the next day, I would mount these on a slide, a gelatin sub-slide, and using an Allen Atlas section images between 70 to 26, which is pictured in the top right here, I would mount those on, put 4 mounts of sections on there. Now the reason I use these areas is because this showed us the most area for the thalamus, and previous studies in the lab have shown that the thalamus is a good area for these microbleeds in the males, so I wanted to do a better comparison, and this was a good section area to look at. From there, I would do my Prussian blue staining, and what Prussian blue staining essentially is doing is it allows us to detect the microbleeds by staining for the iron deposits that occurred from the bleeds. And so Prussian blue has a compound called ferrocyanide, which actually binds to the iron and allows for the blue pigmentation that we'll see in future slides with the brain tissue. Nucleophast red or paracetamol solution was used as a counterstain to help clear it out. And then add 50 to 100% ethanol in a range was used to help clear out the excess of the counterstain, and then two times of xylem were used to help differentiate the Prussian blue further from the nucleophast red. Finally, we were able to actually taking pictures, and if you all knew where I was, my third home, other than 417 in the lab, was this small room, and I would be taking pictures for at least hours on it. And I would take pictures about at 10x scale and at 40x scale. The 10x scale pictures were then put into Photoshop and merged together into this beautiful picture you see on the right of the brain. And the 40x pictures were used to help us see the microbleeds even closer to to detect them qualitatively better. To quantify the bleeds, NIH MHJ analysis toolkit was used, and color spectrum was coordinated to allow for picking up only values that were associated with the pigment. Finally, a sex difference comparison was made, and this was done using prior studies in the lab done by Yanda Wang, who was a master's student here previously last year, and she did the male studies. And so I did a comparison between the aging of the males and the aging of the females. Finally, for statistics, a graphic prism was used, and a one-way ANOVA with a two-piece multiple comparison test was used for all 4 cohorts of the females, and then multiple t-tests with Homestead correction was used to compare the averages of the males from the Yana's data to my averages in female data. Right? So those are my methods. Now we'll get into the fun part, the actual data that I collected. So this is the first big data that we're going to see today. It's the microbleeds for the aging females. So as we can see here is that with age, we don't see any differences between the young and middle age group, but we only start seeing the changes at old age. And old age is where we start seeing significant changes compared to the middle and young. Now to make sure this is a little more accurate, I decided to look at this with brain weight. So I took the brains of the brain for each, and I looked for the, I wanted to use that as a relative signal. This is good because what we see here is that the weights don't actually change over age. There's no significant change at least. And so I could use this as like a baseline comparison to create a ratio between the microbleeds and the brain weight. And we're seeing that this difference we saw earlier is actually a lot more prevalent in the old females compared to the young and middle age. Bringing this together, we see qualitatively as well that this occurs as well, where the young females don't see any bleeds, the middle-aged females do see, start seeing some bleeds, and then the old females see a lot more bleeds. So putting this together, we're seeing that at the young and middle age, we don't see any difference. Statistically, we don't see no difference in the amount of seeing bleeds. But at the old females, we are seeing this difference in both the young and the middle age. So this kind of can lead us to saying that aging alone can show increase in CMVs, but we only start seeing this at the old age. So now we're looking into comparison with the old males. So remember, I did do a composite control of old males at 3, and we're seeing that the old males are significantly different. The most important aspect is this piece here. We're seeing that the old male is significantly higher, has higher microbleeds compared to the old females. This, so that's important to notice. And then we're comparing this to Yana's data on her microbleeds with the aging from young, middle, and old. We're also seeing that at young there is no difference, but at the middle age we are seeing a difference. And then at the old age we are seeing even further differences too between microbleeds between males and females. On a time course, if you now apply this as a time course, we're seeing that there is an actual, both are exponentially increasing with age. But what's important and interesting to see is that the exponential increase in males is a lot more, or is a little more higher, or a little more steeper than it is in females. Which is interesting to note that, and which is showing us that males are developing microbleeds a lot quicker and a lot more over time compared to the females. And this is important at the old age because if, according to my hypothesis previously, it would have actually shown a much higher increase, but we're not seeing that here. Qualitatively, between old males and old females, we're seeing that yes, they both have they have a good amount of microbleeds in both. However, the old males are more dispersed out, which do tend to have a lot more bleeds. So in summary, for the sex differences in CMVs, we're seeing that females of all ages have significantly lower amount of bleeds compared to both the control and just in general male cohort. And those differences in cerebral microbleeds are shown further in old age. And the rate of increase is exponentially higher with age in both sexes, and the higher rate is in males compared to females. And then we also see that females start developing significant amounts of bleeds only at old age, while males start beginning this at middle age, which is important to note. because this could kind of help us with understanding the conclusions we can draw. The first is that females did not seem to have any significant bleeds until old age. And this could be because there's a potential protective factor in young and middle age females. Studies have shown that this potentially could be due to estrogen cycling, and that females have. Further research has show that. Also, there's increases in CMVs at middle and old age males. They are compared to the females, and so this could again be because there is a protective factor at the middle age that allows for the levels of microbleeds in the females to be low and have significantly lower than the males. And then finally, there could be connections made based on prior research between cognition, dementia, and stiffness in females. But this has to be tested further. Prior research has shown that there's possible connections between CMVs and cognitive decline, as well as between hypertension and CMVs as well. So there's both a cardiovascular aspect that can lead to the cognitive decline as well. But future studies have to show this, and that's kind of what we're getting at next, is that future studies should have cognitive studies in both sexes to look at novel object recognition tests, which test for episodic memory, and elevated plus MACE, which looks at spatial memory. Because studies have shown that there are differences between the sexes in this as well. Important to do as well is that we should increase the N of the mice that are used. Because, for example, one thing that I should note is that while I did a comparison between Yana's work and my work, because of user methodology differences, we do have slight different variable numbers. This is shown based on the fact that my old age male mice had a slightly lower amount of bleeds compared to her old age mice. So having a continuum of a larger number and in one study showing both male and female will help further show this connection between the differences in male and females. And then finally, exploring potential mechanisms is what's important, including hypertension, inducing hypertension, and then also looking at the APOE knockout gene, because the APOE gene has been shown to be connected to both dementia as well as cerebral microbleeds. So looking at the knockout mice model for this could be a really good next step to identifying a genetic marker for both and helping put a connection to it. So finally, I'd like to end with the importance of this current study. This is a kind of novel study because, again, it's the first to show sex differences in CMVs in the mice. Clinical studies have shown differences in female, but it's very but in the research in mice model there isn't that many, or there's none, as far as I'm aware of. And I did a literature search yesterday night, so that helps. In research, we should start identifying mechanistic differences in the sexes, and that can be helpful looking at cerebral microbleeds. And then clinically, we can start looking at developing treatments that are specific to sex, so that we're not over prescribing medication to a female patient when it's not necessary. With that, I would like to acknowledge a few people before we get into the questions. First off, Dr. Catherine Morgan for kind of taking me on about a year and a half ago and keeping me on task throughout all the times that I wanted to do something else. And Dr. Dustin Allen, he came in just now, it's 9 months, has been 9 months only, and he became a second grader, and he was actually my teaching mentor, and I owe him a lot for everything the past year or two. My parents, obviously, they're going to be watching this later on video, so thank you for everything you've done for me for the past 24 years. Sargent College, my lab mates, Dr. Khalid Singh, Dr. Loba, Prasvati Reddy Kulajuri. I think I said that. I'm hoping I said that right. Yeah. Good. Yixing, who just finished her master's last week and is doing a PhD now as well in the lab. And then the undergrads, and Kim, Kumar Patel, and Emily Thunberg as well. I also would like to thank Yanda Wang, who, as you see, she's a big part of why this research existed for me, and she helped teach me my methods at the beginning. So I really wouldn't be here without that. And then obviously the whole department has been welcoming to me since day one. special shout out to Donka, Dr. Shawland, and Diane Wadman, who have always been there to help me with the administrative aspects as well, and just giving me general life advice too. I also like to thank my cohort of students, Julia, Jack, Andrew, Jesse, Rachel, Kate, and Mandy. They've all been there emotional support, and we've had tears, cries, laughs, drinks, everything. And then last, I want to thank Sargent Swartz, a new friend I made the past year. He was there with me yesterday. I was freaking out, putting this presentation together, and like, oh my god, am I going to do this right? Am I going to do this right? And he's like, no, calm down, you're going to do this as well. And so I really have to thank him for that for yesterday. With that, thanks for coming. This is pretty much all I have. Yeah.